Hi, welcome to the lecture on Chapter 1, Basic Concepts. This one's going to be a little bit generic, only from the standpoint talking about what algorithms are, what pseudocode is, how to structure your pseudocode, along with different techniques for looking at what data is. In this, remember, I am not going to make this a programming class, so to speak, even though the textbook is written in C, where a lot of the programs are. I'm more concerned about you understanding what the different algorithms are and the logic behind them. So I may use some of the programs, but for the most part, you probably will see me skipping past, if you're following with the textbook, the C code. When you're turning in assignments, I really don't care which language you submit them in if you do, whether it's Java, C++. When we get there, I'll let you know and I'll remind you. So let's just look at the lecture on basic concepts for algorithms. So what I'll talk about is the use of pseudocode and how to develop algorithms. Because you have to, before you start coding, you have to understand the logic. And that's what pseudocode is a way of implementing, putting your logic to paper so that you can then quickly convert it into working pseudocode. We'll talk about what an abstract data type is, abbreviation for ADT. So we'll talk about those, how they're implemented, how ADTs are implemented. We won't talk about void pointers and pointers to functions. They're different for each language. This set part is referred to C. And then we'll talk about the role of big O notation, just a way of how do I compare two algorithms, because there's multiple ways of solving a problem. This one just says, okay, which of the two would be better based on the situation. So big O is a way of analyzing an algorithm and determining which would work for you. So let's talk about pseudocode. Basically, all it is an English-like representation of logic. It consists of basically just some basic constructs, sequencing statements, selecting like an if statement or a looping statement or iteration. Things that I'm looking for in some of your pseudocode are what is the header? In that header, what is the purpose, conditions, the pre and post conditions, what's going to be returned from this algorithm. A little bit on statement numbers. Because you got to make sure you define your numbers, what statement is. Naming of variables, how to construct your statements, and then how are we going to analyze pseudocode. Oops. There we go. Go back one. Let's get back. So the algorithm header basically does a couple of things. It's basically four things. The way I've got it highlighted here is one, you got to have an algorithm. It's got to have a name. Behind that name is what is the purpose, a brief description of what this algorithm is supposed to do. And then any conditions. What conditions have to exist before we start, the preconditions, what are the requirements on the parameters and such, and then post conditions. What's going to happen if, what happens when this algorithm is completed running? Data written out to a file, return a variable, call another function, whatever the case may be. And then if the function or algorithm returns something to the calling party, you got to list that. But you got to keep in mind that this header must be complete enough for you to code and understand to be able to use this algorithm. So when you're thinking about developing your header, you got to keep in mind, okay, what are the requirements for using it? What's it going to do? And what do I expect out of it? So that's kind of what this header is all about, is making sure that that's documented. Now, I don't know, most of you have never had the case where you've mislabeled or not identified your software, at least statements. Back when I started coding, it was all key punch cards. And if you didn't number your cards and drop them, guess what you were doing? You were playing 52 card pickup, hopefully resequencing the program in the correct order, and then running it and see if it worked or not. So you got very good at numbering the statements and making sure you had gaps in the statements so that you could insert new lines of code if you needed to. Now, to make things easier, we know we've got indentations in your code. If then else, the statements you can do after an if statement or inside a loop. There are different levels or layers in this code, and if you were numbering your source code in, let's say, like you were doing a paper with Word, and you numbered your paragraphs. Every time you hit a subparagraph or topic, you'd have one more layer of numbers. The same thing happens with nested ifs or nested loops. To make things a little bit easier so you're not writing out 1.2.2 for a statement, you can just type the number 2 under that, and because I could be able to look at that and deduce that it's indented accordingly. Let's see, I thought I put a copy of, let's just take a quick look here. And here's that, 1.2.2, and all we had to record was the 2. And so I didn't require you to put 1.0, 1.1, 1.2, 1.2.1, 1.2.2. You can just put in the 2 to know that it's a lower, indented twice. So the next thing about is variables. One, you got to use intelligent names. It's got to give some meaning to describe the data. You don't have to define variables like you do in programming languages, but there are some general rules. One, just no symbol. You won't see an X or an I. No generic names like sum or total. Abbreviations, they're allowed, but got to be careful. The example I got here is NO capital STU. It could mean no student or number of students, so you want to be clear in what your variable names are. So you got to be able to read the pseudocode and be able to tell from the names and the indentations what those variables are doing. Now, as far as statements, there are 3 types: sequence, selection, and loop. Sequence, it's just one or more statements that do not alter the execution path, one right after the other. Selection, I evaluate and then make either execute 0 or more alternatives. So that would be like an if statement or if then else statement. In pseudocode, there are no case or switch statements that you see in some other languages. And a loop, as you've seen in other programming languages, it just iterates a block of code. Here's just an example of the pseudocode. So here you see title, gives you a brief description of what this is supposed to do. The algorithm reads a file and prints a report. Preconditions, page number is going to be passed. The post condition, the report is printed. And what the page number contains, that's being fed. And am I returning this? Yes, I'm returning the number of lines printed. So you get the title, you get a brief description of what it is, what conditions exist before, what's going to happen after, and what value changes. What return value is going to be. Now, you got a loop, and within that loop, now I see with the loop statement, I've got a loop, and then I've got an end loop. So I'm not worried about braces or brackets in some languages. You're going to tell me when the loop starts and when the loop ends. The same thing with an if statement. You got an if statement and an end if statement. So just keep that in mind. You got to tell me when it's starting, when it ends, because you won't see in an if statement where you can put braces around a sequence of activities or steps you want to do. I've got a number of, and I got to say when this if statement ends, and then return. So you got loops end, if statement ends, sequential statements. And you see the numbering convention starts out at 1, which could be 1.0, 1.1, but I just need you to print the 1, and with the second indentation, start the numbering sequence again. Just another example. Again, preconditions, postconditions. Now this description I would say is kind of invalid because it doesn't tell me what. It doesn't give me a brief description. I mean, it should have said print deviation from the mean of series, but it didn't. But it gave me a precondition and a postcondition, but it didn't give me a return. It is not necessary to have a return statement. I would prefer in this case, I would have had return nothing or 0 or something to indicate that you at least thought it through enough that you said there was nothing going to happen. Because I'm looking for the logic and I want to make sure that you're thinking through everything that could happen. Now, abstract data type. The abstract data type consists of data declaration packaged together with the operations that are meaningful to the data, but it's also embodying or has all the structured principles, so all that structured programming principles of encapsulation and hiding data. So you've probably heard of encapsulation in a lot of different functions, but basically I'm hiding something from the user. I may know the name and what it does, but how it does it, I don't know. Now there are certain things that are different parts of an ADT. And we're going to talk about whether it's atomic or composite, what the types of data, what the types of structures, and a little bit about the data types themselves. So if we look at an ADT, it consists of a data declaration packaged together with operations that are meaningful to the data. Do I have that? I guess I got that. Sorry, I got that one twice. Okay, we'll change that. Now, atomic and data, composite data. Atomic data basically says it consists of a single piece of data, basically something like an integer. In this case, 4,562. It can't be broken down. Some languages you may hear it called scalar data. But basically, atomic data it's a single piece of data. Nothing, you can't break it down any further. Same as you can't break an atom down any further than, except nowadays they're saying you can get electrons, subparticles and stuff. But for the most part, the atom's the smallest part. So this data is this single piece, the smallest piece of data, not intended to be broken down. Composite data is data that can be broken into subfield, like a telephone number, where you get an area code, an exchange, and a number within the exchange. So it has subfields. Now, the data types consist of two parts. It's got a set of values and a set of operations that can take place of that on those values. I'll show you some examples on the next slide here. So here you got integer, and I can do negative infinity all the way up to positive infinity, and adjust the single numbers 0, 1, 2, 3, blah blah blah. And what you can perform on an integer are all of these different values: multiplication, addition, subtraction, percentages, division, so on and so forth. Those are the data types. Those are operations I can perform on those values. Now, floating number means what? I've got decimals, so I can be 0.0, 1.3, 1.7, negative 2.6. And again, what can I do? What operations can I perform? Multiplication, addition, subtraction, division. So all programming languages will define, based on the data type, what its possible values are and what operation can be performed. And then, of course, characters. So I get integer, floating point, and characters. Characters are what? A, B, C, D, uppercase, lowercase. And basically in most operations, most programming languages, I can say what? I can be less than, equal to, maybe a comparison. So that's what we're talking about. We're talking about data types, identifying a type, what its values are, and what operations can be performed on it. Now the type, what is a data structure when we're talking about this? Now a data structure is just a combination of elements which is either data type itself or another structure. I can have a data structure within a data structure. But it's just a combination of all these little elements. And then this set of associations or relationships involving what can I do with those structures. Kind of look at this in a couple of minutes. Here's some examples. An array, that's just a sequence of data or data types known as elements. So each piece of information, you've got elements in each item of an array. And its position, so if I'm in position 0, I've got a value. Position 3, I've got a different value. Records, combination of data into a structure. Position means nothing to a record because what? Usually in most cases a record is the smallest piece to a data structure. Now atomic data type or abstract data type, it's an example would be a library function. You include in your compiling your program a library, and in that is a set of commands that you can use. You know what the input to a command is and what you expect the output. Maybe it's the sum or divide or mean. So you understand a little bit. You know how. You know what you want to do. I want to do a sum. But I don't necessarily want to know how it was done. I want to know the what, but not the how. So I've kind of I've kind of made it a little abstract because all I want to know is what the data type is doing and the how is hidden from us. So that's we're kind of encapsulating the how from the user. All I want to know is what is my inputs, what do I expect as an output. Maybe your function returns that you've written in previous classes. You passed it variables, but you wanted a number back. You didn't care about all the steps in between, but you just knew I needed to put A and B in and expected to get a sum of A and B out. So those are types of things. Now, there are 4 types of abstract data types, at least 4: matrix, linear lists, trees, graphs. We're going to go through a lot of these this semester. Here's some graphical representation of a linear list, a matrix, tree, and a graph. There's some similarities between those, but we're going to be going a lot into each one of these. We almost got a chapter in each one of these this semester. Now, the definition here is, it's got to be total. It's got to be, I've got this data declaration packaged together with all the operations that are meaningful to that data type. So basically, I'm encapsulating data and operations inside this ADT. So the ADT declares the data, declares the operations, and it kind of encapsulates both the data and the operations into one piece. In this section, we're talking about model for an abstract data type. We're going to talk about 2 things: ADT operation and the ADT data structure. So let's look at the operations. Operations, you get, what can I do with it? I can enter data, I can access, I can modify, I can delete, all through an external, where'd my mouse go? There it is. External interface. Each operations has a specific algorithm. So in this ADT operations, you're going to see I'm going to have an input, a delete algorithm, because each algorithm is a little different. So I'm going to put all these together. You're going to have a separate function for each one of those. So each operation there has its own specific algorithm. only the operation name and its parameters are available to the end user application. So when you're calling a routine, you may not know all the application, all the code, but you just know which functions are available for you to operate. So here's a picture. I've got an application program with a particular interface to that ADT. Now, in this ADT, there are information that's public to application program, and there's some functions that are private. And inside that, I've got data structures, whether they're arrays, linked lists, records, whatever they may be, but all of that is hidden. The only thing your application program knows is what's my interface and what is this ADT asked for. What is its input, what's its preconditions, what are my post conditions that I'm expecting for, and is anything going to get returned to me? Now, remember that the ADT must hide the implementation, how it's done, from the user. All data about its structure is inside the ADT because there could be a case where multiple versions of a structure may coexist. You've got to make sure you hide the implementation while able to store different data. Some of the examples that we're going to go through in this class: stacks and queues, lists, binary search trees, AVL trees, B trees, heaps, graphs. We're going to go through a lot of these so you understand some of the tools that are available to you to make your programming better. Now, there are basically two ways you can implement an ADT list. In this section, we'll look at basically the list link. You got an array implementation or linked list implementation. Hopefully you've worked with both of these in previous classes. An array, we know, is just a sequential list maintained order of its structure of its data. So all the pieces are item 0, 1, 2, 3, 4. And searching an array is what? It's a sequential search. Can be efficient, but what's difficult about array? If I want to add or insert an item into this array, can be inefficient. Could be a waste of time. And because in advanced algorithms, very rarely are they used. But to understand the basic constructs, you've had to learn array, two-dimensional arrays, three-dimensional arrays, just to get you be able to use some other advanced concepts in programming. But for the most part, very seldom used. Now, what is used a lot is linked lists. Linked lists are basically their ordered collection of data, but each element contains the location of the next element. They usually have two parts, a data section and a link section, and there could be more than one link. Could be forward and back, could be pointing in two different directions. So it could be one or more links with some data. Now, you can use to create linear, nonlinear structures. A linear, each element has 0 or more successes, and it's the bigger reason it's used is its ease to add and delete data to it, unlike the array, which can cause difficulties. Now, each element has what they call a node. So we had a little element, had a number in it, and it's made up of two parts, right? Data and a pointer. That's called a node. It's called self-referential structure only because it can have one or more pointers to a same structure type. Now, things that we've talked about, or you will talk about, is things that we need to consider about is a linked list must have a head pointer. There may be additional pointers to make the algorithm more efficient, like maybe last item in a list or item found. And it'll depend on what problem you're trying to solve, whether you're going to have not only the head pointer, but you may want a tail pointer and additional pointers to make your life easier solving the problem. Here's just some graphical pictures as far as your linear list. Basically, it's here's your head pointer pointing to the first element, so you got your data, link to the next item, next item, next item, and then you've got a null link which says that's the end of my list. If you've got a nonlinear list, here I've got 2 links, and then you've got an empty list where there's, hey, nothing, I've got no data associated with it, there's nothing in it. Here's just an example of a linear list. A node to data, or a nonlinear, I can have one or more pointers from a node. Here's just a couple of examples of how they could be used. A number, a pointer, name ID, and grade points, name, address, phone book. So just examples of stuff that you're probably used to using in day-to-day stuff. So now we've talked a little bit about construct of at least the data part of it. Now let's look at how do I determine if an algorithm, how do I compare 2 algorithms? Because there's more than one way to solve a problem. So when I'm designing and implementing algorithms, I got to understand what makes a good or efficient algorithm. And we're going to look at a couple of different ways, principles to use to analyze algorithms. And we're going to look at linear loops and logarithmic loops, nested loops, talk a little bit about big O notation, which is just a way of defining which algorithm is better, and some kind of measurement of efficiency in an algorithm. So algorithm efficiency is one where there's no one way to solve a problem. But I got to be able to compare 2 different algorithms. Now, what we've used is just order of magnitude. If I gave you only 3 items to compare or run through 2 different algorithms, at today's speed of computers, you probably couldn't tell the difference which one's faster, which one's slower. But if I gave you 10,000 items, you probably could tell which one is on an order of magnitude, which one's 10 times faster than the other one. So just when you're comparing algorithms, think about order of magnitude, not any one clock cycle making things better or worse. Now, a linear function basically has no loops, no recursion. So what we want to do is we want to look at, when I'm comparing efficiency of algorithms, I'm going to focus on loops, because recursion, hopefully you've had some exposure to recursion. If not, we'll cover that next chapter. But basically a recursion is I can have one program call itself, basically, and then just go through. But that recursion process I can convert to a loop. So recursion we'll talk about in chapter 2, but recursion basically can be converted to loops. So we're only going to focus on loops when determining the efficiency of an algorithm. Now, linear loops basically says, hey, it's directly proportional to the number of iterations. If I would plot it, it'd be a straight line. So here you'd have function of number of elements equals the number of elements that you've processed, or number of iterations that you've processed. So in this case, it's linear, n equals n to be a straight line. I'll show you a little bit of that. Now, if I had something that would be considered a logarithmic loop, that means the controlling variable in a loop is multiplied or divided on each iteration. So just keep in mind, so as you're looking at the loop, if it's straight, do I to 10, 1 to 10, fine. I'm just going to go through linearly. Function equals the number of terms. So if I equals 10, I equals 100, I equals 1,000, it's a straight line. With a logarithmic loop, it's saying, oh, I from 1 to 10, but you're modifying, you're multiplying that, so it's 2 times A, 2 times B, 2 times, whatever the case may be. Once I start multiplying it or dividing, it's a logarithmic loop. Now, we've all you've probably seen a nested loop, and basically all I got to do is, with nested loops, I got to determine how many iterations each loop completes. So basically means what? The number of iterations means outer loop times the inner loop gives me some counter. So it could be, 2n. If it's 2, a loop, like for x 1 to 10, and inside it's y 1 to 10. In that case, it'd be outer loop is 10, inner loop is 10, total iterations 10. So you get your idea. Linear logarithmic, because we said what? Logarithmic is it's a multiplication, but it basically says the outer loop is linear loop and the inner loop is logarithmic. So you got an outer loop that would be linear, so it's I to 10, where the inner loop would be logarithmic, which means you do some kind of multiplication or division on each element. Then I would define that function to be n log n. So you got log n based on the logarithmic part, n based on the linear part, n log n. So when you're looking at those nested loops, you're looking for things like that. Now, there are cases with nested loops you could see a quadratic loop, and basically it's the inner loop is executed the same number as the outer loop. So in that case, you got n squared. Now, a dependent quadratic loop, the inner loop depends on the outer loop. So I know there's probably more math than most of you care to do, but I just want to give you a feel for there are different ways of looking. So when you're looking at the loops in your program, you're going to pay attention to, is it linear? Is the loop, is there something happening to the controlling variable by multiplication or division? If there's multiple nested loops, is the inner or the outer, and how are they being manipulated to fall into some formula like this? Now, when you look at this, it's like, well, how do I determine this? Well, I'm not concerned when you're trying to do this big O, and that's really what we're trying to do. Big O says, I'm just trying to find this big order of magnitude. What's the big order of magnitude between this algorithm and another? So I'm not looking for an exact measurement. I'm just looking for that general order of magnitude. So usually what I'll do is I'll set all the coefficients of terms to 1. So there's no big multiplication factor going on. I keep the largest item, throw the rest away. Because that largest item, the one that's going to grow the fastest, which would be, that'll be the driving factor to this order of magnitude. And then I would rate all the terms. And here this gives you a rough idea, log n, n log n, as far as largest, smallest to largest, as far as the different types of algorithms. So you're looking at each one, and then you're ranking them. This gives you a rough idea if I'm multiplying, dividing loops, number of iterations, and the values. So you can see they can grow pretty exponentially by that. And then if I plot these, you can see where you got big O's on the y-axis, the x-axis is just the number of iterations. Here it gives you log n, there's n log n squared, n cubed, showing you based on if I was going to choose between algorithms, one that's n cubed and one that was log n, guess which one you choose? You'd want to choose the log n because it'll be more efficient, run faster under large quantities of data. So a couple of examples. Here we're doing and adding matrices. So how do I add a matrix? You got x1, let's say you got x and y, x1, y1, added one matrix added to the other, so it's on an element by element. So the 2 and the 1 are added, the 1 and the 7 are added. So all of these things are straightforward. So here's an algorithm for adding two matrices. Again, here's a title. It's all the input variables. It gives you a description. It says add matrix 1 to matrix 2. So here's matrix 1, 2. And place the results in matrix 3. I would probably also define what size meant, but just we know that now it says the size probably is the elements. This is a square matrix. that size would say, oh, is it a 3 by 3, 4 by 4, 8 by 8? And then it gives you what are my preconditions. I got matrix 1 and matrix have data in size is in columns and rifts in matrix. And then the posts are the matrices added and result in matrix 3. So from that brief description, you can tell basically what this algorithm is going to do. Now here you've got a loop. Okay, it's going to end, not the end of the row. And inside, that's what I'm going to do per row, and then each column. And then I'll add matrix 1 and matrix 2, and store that in matrix 3. And that loop, and this loop, and the routine all together. So it's not a complicated, so I'm looping one versus the other. Now, when I think about that, it's just, okay, this is a classic quadratic loop. Basically means I'm adding each element of quadratic. So it's totally based on, I've got 2 loops, and based on whatever size is, or in this case the number n, so it would be n squared. So when you look at this algorithm here, this is the size, this is size, or in this case n, do these steps, I'm done. So n times n gives you n squared. So order of magnitude, it would depend on the size of the array on how fast it would operate. Oops. Again, now let's look at matrices again, but now look at multiplying 2 matrices. And basically what you're doing with multiplying 2 matrices, I am multiplying the row of one matrix times the column of the other, item by item. So I've got 4 times 6, I'm adding together 2 times 3, I'm adding that to 1 times 4. That solution ends up getting put in the first element of the resulting matrix. So row times column on an item by item or element by element basis, and store those in. So here's your algorithm, or at least part of it. So I've got a loop. Right now you see loop, loop, loop. So you got 3 loops, calculation, storing. So I really don't care about these elements in here, these items inside that middle loop. So I'm going to worry about, I got 3 different numbers here. I got what? Since it's a square matrix, I got these 2 end up being the same size. So you probably already see that as kind of an n squared. And now I've got this size of times, how big is those elements? So here, you say, well, gee, size is probably going to be smaller, but you don't know that for a fact. So basically, since I have 3 nested loops, you're going to have a cubic loop or n cubed. So it's kind of, so when you look at these, and you get a chance to play with that. Oops, lost the end of that. But I'm hoping that helps you a little bit understanding what we're going to talk about in this class, and you'll have to let me know in your feedback, is this lecture good, bad, or indifferent for you. Have a nice day. Bye-bye.